All right, so let's go ahead and get started. First, welcome back from spring break. I'm sure you all had a lot of fun. Like I said, things are going to change a little bit in this class since we've come back from spring break, and we're going to do, I guess the best way of saying it, we're going to do some real finite element analysis from now until the end of the semester. And what I mean by that is no more of the Excel and theoretical, deriving shape functions and all that stuff. No more of that. Everything that we did from day one up until now was to give you the fundamental, background material to be able to do real applicable finite element analysis, and that's what we're going to do starting now. Now, the program that we're going to use is FEMAP, which is what you all have opened now. I want to talk to you a little bit about how these programs work and some of the things that these programs can do. I really want to convince you that when I say real finite element analysis, I mean it. Okay? So let me talk a little bit about how finite element modeling works in software land and in computer land. Typically, the way we define how finite element modelers and programs work are in three phases. So the first phase is what we call pre-processing. And pre-processing is where you actually create the model. You create the geometry. So if you're doing like a beam analysis, that's where you actually draw out the beam. Its length, its width, its height, and all that. Or if you're doing a gear or an engine or whatever, you actually create the geometry. And then you go in and assign, if this is an engine, that part's aluminum, that part's steel, that part's copper, that part's whatever. You go in and assign the material properties. The element types. Is this element a shell element? It is a plate element. Is it a bar, a beam, a isoparametric element? Is it 2D, 3D? That's where you go and assign that stuff. Okay? Now, the numerical analysis is what happens in the background. And to be honest, the numerical analysis is what we've spent all semester really trying to understand, which all in all, for the purposes of what we do in this program, is just hit go, And I know that's going to seem like we spent 11 weeks figuring out how to hit the go button. Well, true but not true. I mean, when you start assigning element types, you need to understand what those element types represent. It's your job as the analyst, given this real-world problem, to create a model that represents what you're talking about. You need to have an understanding of how this stuff works. Okay? So what is the numerical analysis? That's the engine that actually runs the program or runs the model. So it numerically integrates all the elements. It assembles the K-matrix. It solves for the displacements or eigenvalue approaches or what have you. And then it breaks it up and does your individual element response, the stuff we've been doing all semester. The last part is post-processing, actually taking those results and making some sense out of it, looking at the deformed shape, looking at the stresses, the strains, any reactions, looking at contours. How do the stresses change throughout this engine or dam or foundation or building or whatever, and trying to plot this data and actually making some sense out of it. So there's three main modules. Now, there's a number of programs out there that do this: Abacus, ANSYS, NX-Nastran, which is actually the native tool that we're going to use today. But you can use multiple packages to do this stuff, and they all tend to follow this same general philosophy. Pre-process, create the model, run it, look at the results. Now, I like FEMAP because FEMAP works with all of these packages. FEMAP is a pre- and post-processor. It does not run the model, but it will create the model and process the results. And the nice thing about it is you can use it with ANSYS. You can use it with Abacus. You can use it with NX-Nastran, LS-DYNA. So if you're in research mode and your advisor says, well, I want you to use ANSYS, okay, I'll use FEMAP. No, I want you to use Abacus. Okay, I'll use FEMAP. FEMAP works with all of it, okay? So it's a really powerful tool in that regards. Now, one of the powerful benefits of the finite element method and what makes it so powerful is that you can handle things where the geometry is really complicated. There are some programs out there that are better than others in creating geometry. I mean, how many people here use AutoCAD or have ever looked at AutoCAD before, or MicroStation or NX or something like that? You can take those files and import them And you can use that geometry in creating models. So FEMAP is a really powerful package. Now, I'm not the only person that's a fan of FEMAP. I mean, there are other industries out there that use this stuff for real analysis. I mean, I pulled this off of the FEMAP website. This is some of the stuff that they've done. So this is a case study from Lockheed Martin looking at some space shuttle systems. And to give you kind of an idea, these are the finite element models that they created for different modules of spacecraft. I mean, this is real stuff. That the program that you're looking at right now, that's what they use to model it. Okay. Now you see here this this finite element image and see all these different colors. Each of these different colors represent the different material properties and parameters associated with each of these parts. So maybe this is aluminum, or this is titanium, or this is some composite, or what have you. You can take care of that with this program. You can also take it down small scale. This is some modeling looking at suspension and steering columns of a Rochester Institute of Technology racing vehicle. Again, same concept, same stuff. This is looking more at a manufacturing standpoint, looking at the actual machining equipment that involved in manufacturing processes. This is, I believe, a tool and die machine or something like that. Although I'll be honest, I'm not 100% on that. I'm not a manufacturing guru. FEMAP can also be used to solve problems beyond just the whole stiffness times displacement equals forces. For instance, you can use FEMAP to do thermal analysis for you mechanical folks that like heat transfer problems and things like that, or fluid flow analysis, computational fluid dynamics. You can do that as well, and what have you. This is a really powerful package, and I think we're going to have some fun with it over the next few weeks. Before we start having fun with it, we need to know how to use it. Okay? So what I've done is I've prepared an example. This is about as simple as it could get. Now, to hell with finite elements, you all should be able to solve a problem like this. For instance, here's the beam. If I asked you what's the vertical deflection right here, before you even walked into my class, you should have been able to do that. Now, so this is a pretty basic problem. Now, I have shown you all how to analyze this type of problem using finite elements. Now, particularly, we're talking about beam elements. What we're going to do here is we are going to literally create a three-dimensional model of this beam. I mean, X, Y, and Z. We're going to create the whole thing. So let's go through the parameters so that you all have an idea of what's going on. It's made out of steel, so 29,000 KSI, Poisson's ratio is 0.3. It's a fixed beam. It's 2 inches tall, 3 inches wide, and it's got a 0.2 KSI or 200 PSI pressure load on the top. Okay? Now, I'm going through all of this because I'm going to make a statement right now that's going to surprise you. What unit, or let me ask you a question, what units do you think FEMAP uses? What unit system? Just guess, anybody. The answer is FEMAP does not use a unit system at all. In fact, many large-scale finite element packages do not employ a specific unit system. The idea is you're the analyst. You use whatever units you want, okay? You just have to keep track of it. So, we're not going to say that this beam is 3 foot long. We're going to say it's 36 inches long. All of our length units are going to be, for our purposes, are going to be in inches. All of our force units are going to be in kips. So whatever value that you choose to use, is fine. You just need to make sure that you're consistent. So let me ask you this. When we get our results from this problem and we look at deflections, what are our deflections going to be in? Inches, right? What's our stress going to be in? Stress. What is stress measured in? KSI. Okay, you see what I mean? That's the stuff you've got to be consistent with. Okay, it's same units going in equals the same units going out. Now we could easily put in 29 million and put a load of 200, and then our stresses would be in PSI. It doesn't matter as long as you're consistent. Okay, make sense? Now, one thing I'm going to do just for the sake of simplicity, and you all can put this on your slide if you want. I hope this shows up. is I'm going to do this. Oh, it's horrible. What the heck? Very good. Is I'm going to do that, okay? I'm making it a point before I even open that program and do anything with it, I'm making it a point to indicate that I'm going to say that my x-axis is along the length of the beam, my y-axis is vertical, and my z-axis is in and out of the page. The reason why I'm doing that is because when we start actually creating this, we need to make sure that we're consistent with what we do, okay? That's one sort of, piece of advice for somebody who's been doing finite element modeling for quite a while is make sure you sort of set up your coordinate system, your origin, right off the bat. You've got that stuff in your head, your life's going to be a whole lot easier down the road, okay? Yeah. Oh, I'm sorry. Did I not give them to you? I'm sorry. Whoops. I get so carried away. Should be enough there. Should be enough there. Excuse me. Probably be a good idea if I pass the sign-in sheet around. Now, one thing just before we go ahead and actually get started, one final thing, I am recording this, okay? So I'm sure there's going to be some of you that are, over here, well, wait, what button did you pick? Or how did you find that menu? I understand that, okay? That's fine. That's why I record it. So if you miss something, no big deal. You can always go back and watch it later, okay? All right. So let's actually go to YouTube, or YouTube. Let's go to FEMAP and actually start to create this model, okay? Let me erase all this. All right. Come on. Okay. Okay. So you all should see a window. It looks something about like this. You can turn the tip off and what have you. All right. You all should see a window that looks like this. So just to go through the basics, so we're actually going to see our model creation right here. This is sort of a model tree info where we can see, okay, how many materials did we create, how many loads have we created, how many boundary conditions, what have you. And this is just sort of a log of what we're going to see here in a little bit. Now, right off the bat, before we do anything, I don't know if you notice here on mine at the very top, do you all see where it says top, right, front, bottom, left, and what have you? If you look, if you right-click up here, there should be a menu that pops up. These are the toolbars that pop up. If you don't have View Orient checked, like check that now, because I'll show you what that is. That's sort of a quick way of orienting your view, so you can view your model later. Like we'll be able to see things about the X, Y axis, isometrically, Y, Z, and what have you. That'll be important later, and it's important for if you're doing a really complex model later on. So everybody good? Okay. So you all have the beam image in front of you. So let's talk a little bit about how we're going to go about this model. So if you look on the very top, you see like File, Tools, Geometry, Connect, and all this stuff. The first thing that we're going to do is create the geometry. Now for this model, the geometry is incredibly simple. It's literally a rectangular prism, a box that has a length, a width, and a height, right? So what we're going to do is, if you look at my screen here, see how we're in the XY axis? We're going to create a rectangle, and then we're going to extrude it. So it's like, you create a rectangle, then stick it out. All right, so this is the x-axis, this is the y-axis, z comes out like that. How long should this rectangle be in the x direction? 36. How long should it be in the y direction? 2. And then we'll extrude it a distance of 3. See? All right, not too bad, right? Now, okay, so if you go to geometry, you're going to see a number of things. So you can create key points, if you want to do like an object snap feature for those of you who are familiar with like AutoCAD or MicroStation, basically if you've got a bunch of important points in your model, create points and then you can snap to them. You can create one-dimensional objects, i.e. curves. You can do lines, you can do arcs, you can do circles, you can do splines, and what have you. So you can create one-dimensional objects. If you're doing like a truss analysis, a truss would just be kind of a bunch of curves. You can create two-dimensional objects, i.e. surfaces. So we can create surfaces with corners, edges, and what have you. You can create solids, volumes. You can also import geometry. What we're going to do is we're going to create a surface and then extrude it out. So I'm going to go to geometry, go to surface, and then I'm going to create my surface by specifying the corners. Does everybody see that right there? Okay, so we'll click that. And you should have seen a little box pop up down here. Okay, now let me explain how a lot of the dialog boxes in FEMAP work. You input a value and then hit enter, the box will sort of pop up again, and it'll keep doing that. And it'll keep working like that until you hit cancel and tell it to stop. So what we're going to do, see how it's asking for a first corner of the surface? We're going to put in 4 corners of the box and then hit enter, and the box will be created, and then we'll close it out. All right? Now the way that we're going to do this is we're going to almost work around it like a clock, like start here and then work our way around. Okay? So we'll keep it simple. The first corner I'm going to say is at the origin, 0, 0, 0. Okay? So I hit enter, and then now it's asking for the second corner of the surface. Y'all see that? Okay, now I'm starting here. I'm going to say my second corner is all the way over here at the end of the beam. So maybe I should put 36, 0, 0. So I'll type in 36. Dimensions look right. Hit enter. Now it's asking for the third corner. Now if I went 0, 0, 36, 0, what do I need for the next one? 36, 2. See where I'm getting at? And I put the 2 in the y dimension, right? So hit 2. And what's my last corner? 0, 0, 2. See that? All right. Then hit OK. And what do you see here? Now the surface is there. So we'll walk around and see how everybody's doing. You have to put a 0 there. Now hit enter. There you go. Now, once you see the rectangle pop up, hit cancel, because now this is what I was talking about. FEMAP's like, okay, give me another one, give me another one. Well, I'm done, so hit cancel. Okay? Does everybody have this? Okay. Now, y'all know on Microsoft Word or Excel, you know how you hit Control A and that selects everything? If you hit Control A, it centers your zoom, so you're centering the whole thing. So pretty straightforward. And if you want, you can actually take your mouse and click inside the screen and sort of rotate it around a little bit. All right? Now, this is not a three-dimensional beam because it has not been extruded yet, has it? Okay? So now I need to do that extrusion. Now, in order to keep things simple, I'm going to go back to my top view. So remember that little toolbar up here I told y'all to create where it says top? Now that puts me back in that XY plane. Y'all see that? All right. So now we need to do an extrusion. So, excuse me. I'll go to, let's see, geometry, solid, and then extrude. Does everybody see that? Okay. So we see this little dialog box. Okay? So a couple things that we need to indicate. So you got to keep in mind, FEMAP is one of those programs that it likes to be as general as possible. So there's a lot of things that you would think, well, of course I want to do this, that you actually have to specify. Because FEMAP wants to be as general as possible. Okay? So a couple things in this extrusion option are along a vector. Let's take a look at this along a vector. What direction do we want to extrude? in the Z direction, in and out of the paper, right? Or in and out of the screen. So I'm going to hit a long vector, and then I get this little dialog box that pops up. And basically it's saying my starting point and my ending point. So if I start at 0, 0, 0, I need to end at like 0, 0, 1. Well, you could do that, but you'll see where I'm going to take into account here in a second. But I'm going to say 0, 0, 0 and 0, 0, 1. See, at this point, it doesn't matter if you put 1 or 100 or 846. Basically, what FEMAP is asking for is what direction do we want to do this extrusion. And we want to extrude this way. So from 0, 0, 0 to 0, 0, 1, that would define that direction. Okay? So I'll hit OK. So now it knows what direction to extrude. It probably also needs to know what it's going to extrude. So see where it says surface? I'm going to click surface, and then it's saying, well, what surface do you want? Look what's happening. See how I hover in here, and it highlights pink? Y'all see that? You can click the surface, and now it knows what surface to extrude. Hit OK. And now we need to know what depth. What depth? 3. Hit 3. And you hit OK, right? Go ahead and hit OK. Now, it doesn't look like anything happened, right? What about now? Pretty cool stuff, isn't it? Everybody have a beam? Whoa, what happened there? Oh, whoa. Oh, okay. All right. You might just have to start over in a little bit, all right? Okay, all right, all right. Just watch along with me, all right? I don't know what happened there. All right. What's yours look like? Oh, there we go. All right. Sound good? Everybody good? Now, what I'm going to go ahead and do is start actually creating some of the loads and constraints associated with this model. Now, we'll start off by doing the constraints, because that one's simple. Now, FEMAP refers to them as constraints. You probably know them as boundary conditions. It's the same thing, okay? Now, this might seem a little silly, but if you go to Model and where it says Load and Constraint, you see this right here? The first thing that you see is these options called Create and Manage Sets. Now, the easiest way for me to explain that, and I apologize to you mechanical engineers, but the easiest way for me to explain that is to use a civil engineering example. In the world of structural engineering, we don't think of things as simple as just here's your stresses and here's your resistance. We don't think of things that simple. We tend to break up loads into different categories. So civil engineers, they'll look at things like, okay, here's the snow load. Here's the wind load. Here's the load due to the earthquake. Here's the load due to the self-weight and what have you. So in FEMAP, I might create a load set for dead loads, a load set for snow loads, a load set for live loads. You could do the same thing in mechanicals. Maybe you create a load set for all your thermal loads and a load set for all your applied loads and what have you. You can do the same thing for loads as you do for constraints. You can create a different set of constraints. I'm just going to keep it really simple, okay? It's just something you have to do. So I'm going to go into Constraint, and then I'm going to hit Create Manage Set, and then create a new one and call it whatever you want. Call it Boundary Conditions. It doesn't matter. You can even, don't even name it at all if you don't want it. That'll be fine. And hit OK. I just went and created a set. You'll know you did it correctly because you'll see a C1 right here. Y'all see that? That tells you as the analyst what constraint set you're dealing with. Like if you've got 8 different sets of loads, you'll see an L1, an L2, and an L3, and an L4. I'll tell you which one you're dealing with. Okay? Make sense? All right. So here's my model. What are the constraints for this problem? You tell me. I mean, look at the model and tell me. Everything's fixed over here, right? So we need to create a fixed boundary condition. So what I'm going to do is this. I'm going to go to Model. I'm going to go to Constraint. And then look what it tells me I can do. I can create a constraint on a point, on a curve, on a surface. What do you think I should do? On a surface. We'll make that whole surface fixed. So on surface, and then watch what happens. Look what happens. See how I'm moving my mouse and it's trying to figure out which surface? That's the surface I need right there, right? Click that surface, hit OK, and look what pops up. I get fixed, pinned, and then I can go in and say, well, I want you to restrain it in the X direction, the Y direction, the Z direction, or rotationally in the X direction, rotationally in the Y direction, so on and so forth. I can get as fancy with it as I want, right? We'll just say it's fixed. And you can title it or not. It really doesn't matter. We'll call it fixed support. And hit OK. And then close that little dialog box. And if you rotate around, you should see something that looks like this. Oh. Actually. You all see that? Bunch of F's on that flat support. That indicates that that surface has been fixed, right? Yes. Hit cancel. Yeah, that's probably what it was. It hit the line. And then you can call it whatever you want. It doesn't matter. Oh, you selected more than one surface. All right, what we can do is this. All right, so let's say you screwed up and you applied boundary conditions in too many spots. I'm not saying you screwed up. But one thing to point out, and let me show you all this on the screen, that's what this model tree is for. So watch this. I'm going to go into Model, all right? Click that down there, and now we see a number of things. We see elements, materials, properties, loads, constraints. You should see a drop-down list associated with constraints. So what you can do is go down that. There's that first set that I created. And then here's my constraint right here, that fixed support. Go in and delete it and start over, Let's say you completely messed up the model. No, I'm just kidding. Well, see right here, you only have one surface there, which is good. See where it says that +5? You probably had +5 and then like... You can call it whatever. Let's check it out. Yep. Yeah. That's when it's thinking, oh, give me another one. So you have to sort of tell it, no, I'm done. So, all right. Is everybody good? So again, if you hit the wrong surface, that's no big deal. Okay. So I'm going to go back to that isometric view so that I can do that. Okay. All right. Those are the boundary conditions. Okay. Now let's look at the loads. What loads are applied to this beam? We have this 0.2 KSI. It's a pressure load, right? It's a pressure on top of the beam. So what I'm going to do now is I'm going to go back to, let me collapse this up a little bit. Let's go back to Model, Load, and now let's create a load set. We'll call that, I don't know, Applied Loads. We'll hit OK. Close that. And now look what happened up here. Now you have an L1. So if you had like 8 different load sets, now you know what load set you're in right now. Make sense? Okay. Everybody good? Now we're going to create a load. So let's go to Model, Load. Which one do we do? Load on surface. Okay? Same deal. Okay? Which surface are we going to pick? We're going to pick this one right here, the surface on the very top. There we go. That one right there, right? Select that surface, hit OK, and then look at all these different load options that you can apply. I mean, some of this stuff's ridiculous. I mean, you've got force per area, moment per area, enforced rotation, enforced displacement. We've got temperature loads. We've got heat flux, heat generation, convection. We've got fluid pressure. We can apply humidity if we want. I mean, we can get pretty fancy with this. Which one do we need to apply? Well, we can do pressure, an easier one, force per area. Yeah. All right, so we'll do force per area. We need to give it a title. Let's call this distributed load. Now, let's test those spatial skills. We have an Fx, an Fy, and an Fz. Which one do we use? Which one do we put the value in? There we go. Say it again? Minus Fy. It's in the y direction, but it's going down. So what we do is we go in Fy and we put in negative 0.2. Again, consistent units. Negative 0.2. And hit OK. And then close the box. And you should have something that looks like this. Now we've got, you can see here, I've got the top of the beam and I've got that pressure load being applied on top. And let me tell you, you can get real fancy with loads. I mean, you can apply triangular loads. You can apply loads that look like sine functions. You can get really funky with loadings. And I mean, you can get funky with all of this stuff. That's the whole point. All right? Make sense? Okay. Now, this is what I would call the geometry definition and the load definition. What else can you tell me about the beam? Tell me something else about the beam that we haven't used yet. It's made of steel, right? Exactly. We need to define the material. So we need to go in and define material properties. So now I'm going to go to Model. We've done the loads and constraints. Let's go into the material. Okay. Now, just take a moment and look at all of the different properties that you can apply. We can apply nonlinear properties. We can apply creep properties, electrical properties. We can go in and define different properties associated with compression and tension. Nudge, nudge, wink, wink to all those people knowing about concrete. Okay, so we can get pretty fancy. What I'm going to do is I'm going to go in, I'm going to give it a title. We'll call this material steel. And we have two properties that we need to specify because we're just doing a linear elastic analysis. We're not doing failure or any of that stuff. We need a Young's modulus and we need a Poisson's ratio. Young's modulus is 29,000 and Poisson's ratio is 0.3. So I go 29,000 and 0.3. All right. Hit OK. You'll know that things are accepted correctly because watch this. See up here where it says ID 1? This is material number 1. Now watch what happens when I hit OK. Looks like nothing happens, but now it's like ID number 2. Again, it's FEMAP's way of going, all right, give me another one, create another material. You have to tell it, I'm done. I don't need any more. Okay? So you hit OK, or hit cancel, sorry. Okay. So what we've done is we've created the geometry, we've applied the loads, we've fixed the end of the beam, and we've created this material. But one of the things we haven't done is assigned that material and those properties to this model. The way right now FEMAP's thinking, we got a beam, and you've got this material property. We need to combine them together. So the way that we do that is we have to create a property and then mesh this structure, okay? So let's go into properties, and this is where your know-how of what you've been learning all semester is really going to come in. So let's go to model, and let's go to property, okay? Now, this is the important stuff. This is where you're actually defining the different types of finite elements that you are going to use for this model, okay? Now, right off the bat, before we do anything, look at what it's saying. Okay, we're going to define a property, and FEMAP is defaulting to a plate element. We're not using plate elements for this problem. We're using solid elements. So I want to go to element property type, and I just want to take a moment and look at this. I just want to take a moment and take a look at this. All right, so look at line elements. We've got bar elements. We've got beam elements. We've got curved beams. We've got springs, okay? All the stuff we've been dealing with all semester, it's right there. 2D, we've got membrane, all right? Membrane, plane stress, plane strain. Remember all that stuff we talked about earlier? It's right here. We're dealing, however, in this problem with a three-dimensional analysis. We need a solid element. So I'm going to pick solid right here. Now, one thing that's also kind of might seem kind of subtle, look right here. See this little check mark for parabolic elements? Remember that homework where you all had a 2-noted bar and then, oh, what about a 3-noted bar? That 3-noted bar, remember how the shape function was a parabola? These are higher order elements. You can do a 3-noted bar, a 3-noted beam, a 3-noted solid element, and what have you. All right, make sense? Sound good? All right, so we'll hit OK. So now, notice how this thing changed quite a bit. For solid elements, it really doesn't need that much data. All it needs is the material, and really that's it. So if I look here on the right, material, lo and behold, look what's there. The steel that I created earlier. And you don't really have to give it a name. You can just call it element, whatever you want. It really doesn't matter. And we'll hit OK. Now again, it's saying, oh, give me another one, give me another one. You got to tell it, nope, I'm done. Sound good? Again, though, we're in that mode where we have not applied those properties to this. And that's where the next task comes into play, which is meshing. Okay? Meshing is one of those techniques that we really haven't talked a lot about before, but you're going to get some direct experience here near the end of the semester. Remember how the finite element method works. You take a structure and then discretize it into a finite element mesh. And remember, we said this really early on. The more elements that you use, the better your answer will be, but the longer it will take to run. Okay? That's where this stuff's going to come into play right now. So we need to create a finite element mesh for this beam. Okay? Now, there's a number of ways that you can do that, and it's another one of those things you can get as funky as you want. We're going to keep it simple for our analysis here. So I'm going to go to mesh, and we see a number of options here. Before we actually go through and create the mesh, I want to apply what's called some mesh control. And the idea behind that is the way finite element processors work, they do their best to kind of best guess what the mesh should look like. And for a problem like this, it'd probably do a pretty good job because the geometry is pretty straightforward. But you're the analyst, you're the engineer. You might have a better idea of what you want that mesh to look like. You need, let's say, more elements here because you're really concerned about what the stress on this gear tooth is or what have you. The idea is, as the analyst, you're going to specify, the mesh density in certain areas. You want control over what the mesh looks like. The more stringent your mesh control is on a given problem, the better your answer is going to, or your mesh is going to be. In other words, it's going to look more like you want it to. Okay? Now we're going to keep it really simple. We're going to go to mesh control, and we're going to say size at point, size along curve, size on surface, and size on solid. And the idea behind this is, like, let's say we're doing size along curve. We could say, well, I want 4 elements across this curve, 50 across this, 3 across that, and it'll figure it out. What I'm going to do is I'm going to keep it simple, and I'm just going to say I want each element to be a certain size. So we're going to do size on solid. So hit size on solid. It's asking for what solid are you talking about? Well, we're only talking about that one right there. So we'll click that, and we'll hit OK. Now, right. First thing it's asking for is the difference between tet meshing and hex meshing. Tet meshing would be if you were using tetrahedral elements, like think of little tiny pyramids. Hex meshing is if you're trying to turn this into small, like Lego blocks, like little brick elements. This is a very rectangular problem, so we'll use hex meshing. Now, the biggest or the most important parameter for this box right here is the element size. Now it's saying 2.2778 because this program in its mesh algorithms figured that that would probably be a good size. I want better results. So better results mean more elements. More elements mean smaller elements. So I'm going to make that number smaller. I'm going to make it 0.5. So think about it like this. 0.5, the beam is, let's say, 2 inches tall, so that's going to be a fair amount of elements in there. So we'll sit, okay? And say, look what we got going on. 0.5, the beam is 2 inches tall, and look what it figured out. 1, 2, 3, 4. Now, it hasn't actually meshed it yet. All that FEMAP did, FEMAP is kind of giving you a preview of what the mesh will look like. Make sense? Now, if you want, you could do 0.25, you could do 1, you could do whatever. All right? Make sense? Sound good? All right. Now let's actually mesh it. Okay, so we'll go to Mesh, Geometry, and since we're doing a hex mesh, I'm going to actually specify that we're doing a hex mesh on a solid. So we'll do hex mesh. All right? Now, look what pops up. It's saying, okay, we want you to mesh this section. What property are we talking about? Well, that's the property I created earlier. That property has steel associated with it. So it's at this point I'm actually going to create the mesh, and it's going to say it's steel. Hit OK, and bam. Now it's actually created a finite element mesh. You should break it up into those individual regions. Remember how the finite element method works. We're guessing what the solution looks like in between that elements. For an element like this, we're using linear interpolation. So the more of these elements that we use, the better our answer is. Make sense? We now have everything necessary to run the model. So what we'll do, we'll go to Model, we'll go to Analysis. Okay, there's no analyses defined for this problem, so we'll hit New Analysis. Now, before we do anything, see where it says Analysis Type and it says Static? Just drop that down. Look at all the stuff that's there. We've got eigenvalue approach. We've got buckling response. We've got transient dynamic time history, frequency harmonic response. My advanced vibrations folks should know all about that. Nonlinear static, nonlinear transient response, steady state heat transfer, all that stuff's there. Okay? We're just doing just a simple static analysis, just loads, deflections. So we'll hit static and hit OK. You can name it if you want. You can say run the model. Hit OK. So we're using NX Nastran. We could switch that out and say, no, I want to use ANSYS, or I want to use Abacus, or I want to use a LS Dyna, or whatever. We're doing a static analysis. We're analyzing it right here on this system as opposed to a server. Hit Analyze. You have this little thing popped up on the side. And it's done. Now, look at this down here. Look at this. 2,555 nodes. 1,728 elements. So what's this number times 3? 2,555 times 3. Was it about 7,500, something like that? So that system matrix, that K matrix, is only 7,500 by 7,500. You all want to do that in Excel? I really wanted you to get it. I mean, this is a simple problem, and we're talking about a massive stiffness. Done. You know, this is important stuff. Okay. Now the model is done. Okay, it sent the model definition to NX Nastran. NX Nastran ran the results, and they're right here. I'm looking right at them. So what you can do is, for instance, we can leave this open if you want. All right. Do y'all see here this toolbar right here? It's got a beam. It's got some colored squares. Y'all see that? Watch this. Let's look at the contoured response. Okay, so this is the response of that beam. What are these magenta purple values representing? What's the stress like in those areas? Pretty much nothing, right? They're almost zero, right? But remember back to your structural analysis. If you've got a cantilevered beam, you don't have any moment right here. Your moment on a cantilevered beam is highest where? Back here. And look what you've got. You've got your highest stresses on the top and the bottom. Remember, bending stress, highest on the top, highest on the bottom. If you want, there should be a little deflected, deformed view, and bam. Now that's what the beam looks like when it's deformed. And if you want, you can have a little fun with it. Put the one next to it, and it does a little animation. I told you this class was going to be different after spring break. Pretty cool stuff, isn't it? What's that? Did you turn your node numbers on? Or? Oh. That's a lot of labels. When you have models that are really, really complex, what's funny, when you have models that are really, really complex like that, if you turn on the node numbers, like you just hit go, FEMAP will say, I'm done, and it'll shut down because the graphics processor can't handle it, and it'll shut down. That happened to me a few times in grad school when I was running Abacus, that I'm trying to figure out, these interconnectivities on some of these parts, and I would turn on the nodes, and it would just say, I can't handle it, and it would turn it off. Oh, it's just animating from like -1 to +1. It's not actually happening, no. Basically, what's really happening is here's undeformed and here's deformed. So when it's animating, it's just going above and beyond. Now, one thing that's kind of nifty, if you look right here, do you see these two boxes right here where it switches contours to previous and next? If you start clicking those, you'll see your contour changes quite a bit. Y'all see that? If you look down here, what's happening is you're switching to a different type of stress calculation. So this is solid shear stress in the XY plane or what have you. So this is like the shear stress in the beam, or shear stress or stress along the Z direction. There's not much at all, and what have you. But if you notice, what was the very first one that it printed out? Von Mises. Told you this stuff was important. All right? Make sense? We're going to take this, this type of analysis, and we're going to explore it quite a bit. Because, yeah, this is a cool, pretty picture, but as engineers, you're going to need to know specific things. Like, how do I query, like, what is the stress right here? Is it 12.2 KSI? Is it negative 13.6 in compression? How much exactly did it deflect? How do you create plots from this data? How do you, interpolate different, values and what have you? Y'all are going to need to know how to do this, okay? That's the point of what's going to happen for the next little while. We're going to do things like looking at different geometries, looking at, okay, this is a rectangular beam. What if it's a triangular beam? What if it's, a bracket or what have you? How do you do different complex stuff, That's what's going to be the purpose of what we do from here on out, okay? So no more Excel. Well, you might have to plot some data, but no more of that, assembling stiffness matrices, by hand and what have you. What's going on there? Oh. Oh, that is a lot of node numbers, or is that element numbers? Those are the responses at each element, yeah. Cool stuff, isn't it? All right. Remember, you all have your second exam due next Thursday, take home. What do we not have on Thursday? No class on Thursday. We're off to D.C. to participate in the canoe. Wouldn't it have been cool to actually build a canoe? We tried. Well, what happened was we actually tried to build a finite element model of the canoe last year. The problem was that we were using MicroStation, or I wasn't using MicroStation. Who I think it was maybe Bryce that built the mold in MicroStation. And what happened was MicroStation and the finite element software didn't agree. So when we imported the geometry, like we just hit import, and instead of getting a nice pretty box, it was all over the place. Yeah, it was complicated. But what we might be able to do for something like the canoe is if you go online, you know how there's the cross-section profile along each section. We could import that and have it just linearly interpolate it, and we could get a canoe that way. And then use a shell element, just assign a thickness. And well, the thing is, well, I think they use, was it AutoCAD or Inventor or something? Yeah, this would probably be much more amenable to Inventor, you know. And honestly, I'll say this, it probably wouldn't be the, like you couldn't use it as your structural analysis in the report. It'd just be a pretty picture. It'd look cool. So you all keep in mind, before I actually call it and we're done with class, we do have an analysis project coming up. So, you know, what I'd like for you all to do is we're probably going to have like a homework assignment or two on this so that you all have a little bit of practice with it. But I really would like you all to define your own analysis project. Instead of me giving you something, find something you're interested in, you know, and attack it, you know. And I can work with you to, you know, define it so you're doing, you know, the proper amount of work. But find something cool, you know, if you want to do some gear analysis or something, or you want to analyze a dam or something. Have some fun with it, you know. Whatever you want to do, just, you know, I'll work with you to make sure it has appropriate rigor for what needs to be done for this class. But really, just to give you a quick preview of what I'm expecting for the analysis project, what you're going to do is you're going to define a problem in engineering that needs to be assessed. Let's say, for instance, it's the deflection of a beam that has a weird geometry. Well, you're going to run a model using the same modeling technique of a benchmark problem like this. Like, let's say you're going to do your problem using brick elements. So you're going to run the model, and you're going to use different mesh densities. Like, remember how we did 0.5? Maybe you do 0.1, 0.5, and 2. So you have like a really coarse mesh and really fine mesh. You're going to take a benchmark problem to figure out how dense your mesh needs to be in order to attack the complicated problem. So you'll analyze something simple, something that you know, to figure out that your modeling technique is correct, and then use that technique to analyze something that is complicated. All right? It's sort of a standard process in finite elements. Benchmark your analysis against a known result, and then use that same technique to analyze something you don't know. Okay? So, you know, and I'll work with you all to make that happen. But I want to see you all get some benefit out of it. You ain't doing this stuff for me. You're doing it for you. So I want you all to have some benefit. All right, sound good? That's all I got for you all today. I will see you all next week.